So in this video, we're going to examine what the effect of using this squared term here in the variance has, and the reason why we do that. So I've already started a page here where I've rewritten the variance equation, and then the definition that I like to use is how much a population varies around its mean. So I'm going to start by coming up with some data for us, and I decided to use belly rubs. I have a puppy named June, and I measured how many times she let me rub her belly each day. I'm going to call that B_I, and for B1, I got 7 belly rubs, and then 2, 6, 8, 0, 5, 1, and 3. So let's start by calculating the mean. And the first thing we have to do is find the sum. So I'm going to do this in my head here. So 7 plus 2 is 9, plus 6 is 15, plus 8 is 23, plus 5 is 28, plus 1 is 29, plus 3 is 32. Okay, and then the average would be the sum divided by the population size. So for us, we have 8. So n equals 8 for us. So 32 divided by 8 turns out to be 4. So 4 is our mean. And then that's going to be the x bar. So for us, I'm going to call it b bar equals 4. Let's go ahead and plot this. So for the first day, we have 7 belly rubs, 2 belly rubs. Day 3, we had 6. Day 4, lots of belly rubs on day 4, which is good because on day 5, I didn't get to rub her belly at all. 1 belly rub. Oops, I did that wrong. Oh no. Okay, so let's ignore this. I wanted 6 is a 5. So that's a 5, and then down to 1, and then 8 should be 3. Sharpie eraser. I don't have one of those. Okay, and then the trend line, the average line is a 4. So let's mark that across. So just in general, if we're thinking about variance, how much a population varies around its mean, this guy varies quite a bit. And again, our goal is just to figure out some metric that quantifies how much it varies. So I'm going to start by calculating this stuff inside the parentheses here. This is actually what I like to call the deviation. So I'm going to calculate the deviation, which for us, instead of x's, it will be b's. bi minus b bar. And so b1 is 7 minus 4 gives us 3. 2 minus 4 is a negative 2. 6 minus 4 is 2. 8 minus 4 is 4. 0 minus 4 is negative 4. 5 minus 4 is a 1. 1 minus 4, negative 3. And finally, 3 minus 4 gives us minus 1. So I calculated the deviation, the inside of the parentheses here. Now, instead of squaring, first I'm going to actually do the absolute value of this, which we can call the absolute deviation. Okay. Kind of crowding myself here, but it is what it is. And so this is just going to be the absolute value of deviation. So essentially I'm just going to copy these over and remove the minus signs, which gives us 3, 2, 2, 4, 4, 1, 3, and 1. And I will calculate the sum of this. So I'm going to do this in my head the best I can. 3 plus 2 is a 5, plus 2 is 7, plus 4 is 11, plus 4 is 15, plus 1 is 16, plus 3 would be 19, plus 1 is 20. Okay. So let's think about the absolute deviation in terms of the individual deviations here. These actually make sense when we look at our plot. So for the first point, 1, I have to travel 3, that's the deviation, in order to get to my point. So from the mean to the point is a 3. So let's call this the score. And then we're summing up the scores along the way. So for this point, we have a score of 3. This point, we have a score of 1, 2. Here we have 2. This one is a 4. Oh, they're down there, down to the 0. This is also a 4. We have a 1, a 3, and a 1. So this makes sense. So this sum here is essentially adding up all the scores of each of the point. And again, we're using golf scoring, so score is bad. And this sum here has a name. We can call this the total absolute deviation. And the equation for this is going to look similar. It's the sum from I equals 1 to n. Yeah, it is sloppy. I apologize. Hope you get the idea. Of bi minus b bar. This is the total absolute deviation, this equation here. So that's what this number is. Now let's look at the squared deviation. So we've kind of done most of this already, right? We've done the deviation itself. All I have to do now is square this term. So 3 squared is 9. Negative 2 squared is going to be a 4. 2 squared is equal to 4. 4 squared is equal to 16. Negative 4 squared is 16. We have a 1, a 9, and a 1. And let's look at the plot, and these no longer make total sense. Since we're squaring the absolute deviation, this score doesn't necessarily correlate exactly. I'll still write it down. We've got a 4, we have a 9, a 4, a 4. This is 16. This score is going to be a 16, 1, a 9, and a 1. So doesn't make as much sense, but alas, that is actually what we use for the variance. What's the sum of this? Oh boy, do this in my head if I can. So one trick I like to do, so 9 plus 4, sometimes I just put it just to the right here. 13 plus 4 is 17, 17 plus 16, 33, plus 16 is 49, I think that's right, 50, 59, and then 60. And then if I was using pencil, I would erase this, but I'm using Sharpie, so I'm just going to cross that off. Okay, so 60. So this actually has a name as well. Let's call this the total squared deviation. And that's this 60, which you may be able to guess this now. I equals 1 to n bi minus b bar squared. So I would argue that both of these numbers, the total absolute deviation and the total squared deviation, give us an idea of the English definition of variance. So they tell us how much a population varies around its mean. So what are the benefits of the total absolute deviation? Well, I would argue it's intuitive. When I see this 20 here, I know that that means that in total, I have to travel 20 to get to all of my points in total. So I do 3 here, 2 there, 2, 4, etc. This 20 makes sense. I can look at the plot and know what this 20 means. The squared deviation doesn't make intuitive sense. And one thing to note about it is that it punishes outliers. What do I mean by that? So let's say that in my measurements of belly rubs, I had one day where I had, let's go with 54 belly rubs. So 54 belly rubs. And so let's assume that the mean was still 4. So the deviation would be 4. So then what would the absolute deviation be? So I'm going to do DEV equals 54 minus 4 equals 50. So the absolute deviation would equal just 50. But then what would the squared deviation be? Let's use SQ for squared deviation. Would be 50 squared, which is 2,500. Oh my God. So what this means is that if we have a number or an observation that is far from the mean, it is heavily penalized. 2,500 as compared to 50, which would be the absolute deviation. So this is not necessarily a good thing or a bad thing. It's just something to keep in mind. That because we're squaring it, outliers are heavily punished. So in our actual definition of variance, our equation here, you see that we use the squared term. We could have used the absolute deviation, so why did we use the squared? Well, the simple answer is just because I told you so, and specifically it's actually a guy named Ronald Fisher who was the first one to specifically define variance with this mathematical equation. And the reasons will become very apparent later as we get into linear regression. And I'll go ahead and write that down. So one of the great benefits of using this squared term for variance is that math is easier for linear regression. And there are a whole other slew of reasons, but we'll get to those later. So that's the effect of the squaring, and a very unsatisfying reason why. Thanks.